So in this video, we're going to talk about solubility of a substance, okay? Now, most substances, they reach a solubility limit beyond which no more could be dissolved into a solution. And so what do I mean by this? All right. That simply means that for most substances, there's only so much it could be dissolved in any given amount of solvent. All right. And I think most of you guys probably have noticed this, especially if you're like, for example, if you're making your own juice, right? Like Kool-Aid. Um, Most homemade Kool-Aids, at least from my experience, is that, um, you have your cup, you have your water, and then you put in your Kool-Aid powder, right? And so you make the Kool-Aid powder. I guess the most popular color will probably be red. All right, and then after that you add your sugar, right? And so we're adding sugar here. Obviously all this should be dissolving, but most of us, or some of us, likes our Kool-Aid a little bit sweeter, right? um and how this looks like really is just that at the end, sometimes you notice there's this layer of sugar at the bottom. All right, and this layer of sugar is just sugar that cannot be dissolved because you already put so much sugar that you actually have passed the solubility, all right, um, point of the substance. Now, the solubility of a substance is basically the maximum amount of a substance that will, apologize for the bad handwriting, dissolve in a given amount of solvent at a specific temperature. Okay. Now, and so let's be very specific and let's kind of break this definition down a little bit. All right. So remember, solubility is just the maximum amount that a solute will dissolve into a solvent at a very specific temperature. All right. And so which kind of tells us a couple of things. Number one, the solubility of a substance is dependent on the temperature. All right, and I will show you this a little bit later how that essentially looks like. But I think some of you guys probably have already noticed this because for those who are like masters of making Kool-Aid drinks or any type of drinks really that's sugar based, is that we know that if we were to heat up the water first, we could get more of the substance dissolved in there, right? And by heating up the water, you're actually changing the solubility. In most cases, for a lot of solid solutes, the solubility or the maximum amount that it could dissolve increases as the temperature increases, all right? And we'll talk about that a little bit later. But when it comes to solubility, what are we saying basically? Well, this is the reason why essentially if you were to have 100 mils of water, all right, you're only able to dissolve 35.8 grams of NaCl. All right, anything more than that is going to show up as a layer in the bottom of the solution. All right, and this can only happen at 20 degrees Celsius, so approximately room temperature. This is also, the reason why if you also have 100 mils of water, right, you could dissolve 204 grams of sucrose, all right. As I said, it still had to be 100 mils of water and at 20 degrees Celsius, all right. Sodium hydroxide carbonate, right? Sodium hydrogen carbonate, so NaHCO3. Other words, baking soda. All right, so if you at 20 degrees Celsius with 100 mils of water, you can only dissolve 9.6 grams of it. So different substances, the solubility is going to be different. But the whole idea with the solubility is dependent on, obviously, number one, how much water you have, right? More water you have, the more you can dissolve the solute. But then at the same time, the temperature is it's one of the things that solubility is dependent on. All right, so this is what we call a solubility curve. Now, a solubility curve demonstrates how the solubility of a substance is affected by the temperature. All right, so the temperature here is your independent variable. The solubility is the dependent variable, or how the solubility is dependent on the temperature. And you could see basically here where I have the solubilities of several different substances, and all these substances are dissolved into 100 grams or 100 milliliters of water. Okay. Now, what you find here is that there is an increase for most cases of solubility as the temperature rise. Okay, and so I kind of suggested that a little bit earlier, that if you increase the temperature, so like when we're talking about making Kool-Aid, I know some people make lemonade like that as well. What the first thing they do is actually heat up the water and then dissolve the sugars and the powders and whatever the case is into the water, because more of it will stay. But yes, that is the case, and we see this trend that happens most of the time. Now, there are some exceptions. So this solid right here is an exception. All right. So we see that the solubility decreases over a period of time. But also another thing I want to suggest is that anytime you have a gas liquid type of solution, so any gas liquid solution, all right, we find that the solubility decreases as temperature increases. So there's a inverse relationship between gas solubility and the temperature. All right, and this kind of makes sense, and this is one of the also things that most of you guys probably have seen, that this is half the reason why we refrigerate sodas. All right, because the colder the soda, the more likely the gas will remain dissolved in the soda. But then the moment you leave the soda out and it gets into room temperature, then we notice that soda becomes flat. And that's because as the temperature rises within the soda solution, the solubility of the gas will decrease. All right, and so gas is more likely to escape out of the soda solution. So that's why several hours later, if you were to try to drink that soda, it tastes flat. You don't have that pizzazz, the spark, right? And so, okay, so we just finished talking about how temperature affects solubility. Now let's talk about how pressure can affect solubility, and specifically, we're talking about the solubility of a gas within a solvent. All right. Now, pressure cannot affect solids or liquids. All right. It doesn't affect it whatsoever. But it affects gas because gases are highly compressible. Okay, you can compress gases together. You remember they're far apart. And so there's a lot of empty space between them. Okay, but then that simply means that we could squeeze those molecules closer and closer to one another. All right, so that's why we're looking into this, which then leads us to Henry's law. Now, what Henry's law states is that the solubility of a gas is directly proportional to the partial pressure of the gas if the temperature is constant. So this simply means, all right, that if the pressure, if you increase the pressure of the system, all right, then you're going to increase the solubility of the gas. All right, so that means you're going to have more of the gas dissolved into the into the solution. All right, and so how does that look like? All right, so let's say here's our container, right? And let's just say our container is closed. So it's a closed container. I'm closing this up. All right, so here's our solution, and here are our gas particles. Now, particles are always moving around. All right, and so what you're gonna have gas who's gonna be constantly escaping. Okay, but then at the same time, you're gonna have some of the gas particles here, and what they're going to do, they're gonna actually go into the solution. All right, it's dynamic. It's always moving around. All right, it's going to get to the point where they're gonna reach an equilibrium, meaning that you have the same amount going into solution, and while you have some amount of gas leaving the solution. So the amount of solution is going in and out. The rate of the change between in and out is going to be the same. So that's just an equilibrium. Okay. Now, what happens if you increase the pressure? All right. So let's just say I push down against this lid here. All right, I'm pushing it down, compressing the gas closer to one another. By compressing the gas into one another, I'm increasing the pressure. So what happens? Well, let's draw scenario number 2. What happens when I push down this lid? I'm compressing the gases. I'm increasing the pressure. All right, so my liquid is the same. Let's just say my container is now here versus the top. Okay, now we have these gas particles. All right, and what you notice, there's more in here. All right, versus what's going on outside. And it turns out that because you increase the pressure, you got more going in and few coming out. All right, and it's going to get to a point where it's going to stabilize itself. It's going to get into an equilibrium. But the point is that I'm trying to make is that if you increase the pressure, right, you will increase the amount of gas that's going to be dissolved. Okay, and so I'm going back to sodas, right, because sodas I think is a really, really good example of that. I mean, whether you drink it or not, we all have some type of experience with sodas. All right, and so sodas, in order to ensure that it doesn't go flat, especially during travel, and then, and you notice also in the supermarket, there's a lot of sodas that are not in the refrigerator. So it's like, okay, how does this stay carbonated? Well, sodas are pressurized. Okay, very lightly so. All right, and so by pressurizing sodas, you could keep the gas molecules within the solution. All right, and this is actually one of the biggest reasons why when you first open up a soda for the very first time, you hear that noise. That noise is pressure changing. Okay, and so now you're alleviating the pressure that's within the drink itself, and because you're alleviating the pressure that's within itself, now because the pressure decreased, what's going to happen is that now you have gas particles start to leave, get out of the solution. So if you decrease the pressure of the solution, then you're going to decrease the solubility of the gas. And so when we open up a soda can for the first time, or a soda bottle for the very first time, all right, we're decreasing the pressure, and by decreasing the pressure, we're going to have it to the point where the soda is going to become flat because the gas is not going to remain as soluble. And this is half the reason why that after we open things up, we tend to put it in the refrigerator. And when we put a gas into the refrigerator, by cooling it down, we will try to keep the gas soluble into the liquid itself. Right, so it's all solubility, really. That's why we do the things that we do. All right, now we could actually go about and calculate the concentration changes or the solubility changes of a gas when pressure changes. Okay, and this equation is C1 over P1 equals C2 over P2. All right, so let's kind of talk about what each of these things means. So C1 or 2 really is the concentration of the gas in solution. Okay, while your P1 or 2 is the partial pressure of the gas. All right, and just the different changes, right? The 1 is always like the initial, and 2 is always the after part. Now, concentration, and we'll talk more about concentration in a later unit, but the unit for concentration oftentimes is, we have some amount, whether it be like in grams or in moles, divided by the volume of solution. All right, and so that could be like in liters or gallons or milliliters. All right, so that's usually the units of concentration. You're trying to figure out how much of the solute is in the solution, all right, in respect to the solvent, the amount of solvent that you have. So that's concentration. Okay, so let's just kind of do an example problem so that you can see how we'll use this equation, Henry's law. So C1 over P1 equals C2 over P2. All right, so let's look into this example problem. We have, at a partial pressure of oxygen in the atmosphere of 159 millimeter mercury, the solubility of oxygen in the blood is 0.44 grams per 100 mils. What is the solubility of oxygen in the blood at 26,000 feet, where the partial pressure of oxygen is 56 millimeter mercury? Okay, and so let's go ahead and let's rewrite our equation so that way we have it on hand. So remember, C1 P1 equals C2 P2. And now I'm going to go ahead and highlight what I know from this problem. Okay, so I see that at a partial pressure O2 in the atmosphere, 159 millimeter mercury. So that's our first partial pressure. The solubility of O2 in the blood is 0.44 grams per 100 millimeters. That's our concentration. That's our C1. What is the solubility? So I'm looking for solubility. So I'm looking for C2 of O2 in the blood at 26,000 feet. So that's just a random fact. Where the partial pressure of O2 is 56 millimeter mercury. So that's that there. All right. And so now I see that I need to find C2. So I'm going to go ahead and rearrange this equation so to show that I'm looking for C2. And when I do that, it's C2 equals, it's P2 times C1 over P1. Okay. And so those are my numbers I'm dealing with. All right. And so now let me go ahead and plug in my numbers as is. So as I said, I'm looking for C2. All right. And so my C1 is 0.44 grams per 100 milliliters. So I'm going to write 0.44 grams per 100 milliliter times, and I'm going to multiply this out by, let's see, P2. So P2 is 56 milliliter mercury, all divided by, okay, and so I'm dividing this by P1. In this case, P1 is 159 millimeter mercury. So 159 millimeter mercury. So all things should cancel out accordingly. I'll be left with grams per 100 mils, or really just kind of depends on how you put this in the calculator. All right, and so when you put this in the calculator accordingly, you'll get that your answer is 0.15 grams per 100 mils. All right, and so, in which this should be an expectation, right? So you notice is that this is your original pressure, and your pressure is decreasing. All right, started at 159 millimeter mercury to 56 millimeter mercury. So if that's the case, my solubility should decrease as well, where you start out at 0.44 and then now it goes down to 0.15 grams per 100 mils. right? And so that's the way how we would typically use Henry's law, this equation here. Okay.